Hey, hi everyone. Yesterday we have seen SVM a little bit on how it works and stuff. The objective itself is not to get to the detail, get to the algorithms and stuff. Let me be frank, in SVM, the algorithms actually also look a little complex. Um, which makes it much more interesting to get into the details. But it will be too many to be squeezed in, and also at some point we should see look at the relevance with respect to runs with respect to Gen AI, and these are all foundational models which are good because they all come with some level of optimization. So they said everything is underlying basis linear regression only. Here also I would actually say it is linear regression itself, like x plus p, whichever is there, same thing is used. Key thing is wx, instead of using x they're using some kind of function like a h of x or g of x kind of stuff, which is nothing but this so-called kernel function, so that the points that are there are actually shifted in a way that they are actually separable through this plane. Instead of having all the points here in the single plane, they are applying some function, and what they're doing function which also works along the labels, okay, basing on not only x and also y, and basing on the x and y they are moving those points. For example, all the um, all the ones which are labeled green uh, will come up. So they're this function that is applied on them, it basing on the value, y value, that is what it says green, right? So basing on the green value and stuff, all of those points are actually moved up, and something on the plane which says which are red points, basing on the y value, the y value will be different for red and green, right? So basing on the y value, they're moved down, and not necessarily there could be more points, and let's say there is also blue points instead of green, right? There is also blue points, so the blue points can be brought to the plane to one side of it, right? Like some side corner. Then what we could do is we can have multiple planes also to separate it. Not necessarily it needs to be always single plane. Then we can keep then we put points up below and then crosswords, and we can have a plane separating this, and then we can also have divide and conquer. After these two are separated, we can actually separate with other plane the remaining points as well. So that is possible. Um, okay. Yesterday when we were discussing, we also thought of discussing about margin, which actually makes it much more efficient. And from SVM's perspective, I didn't go into the detail on how it is formed and stuff, but when you talk of separation of the points that are there above and below, let's say there is some gap in between, right? Like this is the gap in between these 2 points, right? Your plane that needs to have classification, it can be in this space, it can be here, it can be here, it can be here, anywhere it is there in this space in between, it actually classifies them well. But to be more efficient, what they have come up with is, you pick up a line, and your metric on picking up the line is you look at the loss, right? So it is supposed to be the actual y value is supposed to be here to these points are above, and this actual y values are supposed to be these points are above, but you're picking up here this line in a way that the overall loss with respect to actual to the predicted value is minimal. That's how you pick up that particular plane. As 2 points are on either sides, what happens is the line going here or the line going here will have more loss. So as the line moves to the center, the loss will actually be minimal, obvious, because I mean not necessarily, but basing on the distribution of points and stuff. It depends on the point distribution of point stuff. So what it does is it actually in the SVM, again not getting into the details, it tries to, so if you draw a line like this or a plane like this, these distances in between the top layer to the line and the distances between the bottom layer to the line, these are called margins, right? So that's the distance between the actual values and the predicted values in a way that the loss is minimal. So that will be adjusted in a way that these margins are maximum, right? So the line actually, as I said, the line can also go from here. The points are above and below, and the lines are actually, line is little closer to the y. What happens? The bottom predicted y. Happens is it is little biased towards this prediction, right? This is, let's say this is negative prediction, this is positive prediction. Then if the line is closer to this, that means the liner is actually predicting values much closer to positive. Or if it's going the other way, line is much more favorable to the uh, negative predictions, right? So either ways is a problem. So the optimal way is this margin, if it is margin considering the distance between these positive points and negative points, if it's maximized, then it is actually like the tenant is going in between, right? So it is not it's not overfitting to either of the classes that are there, either of the values that are there, and that makes it a good model which has optimal fitting. And so the prediction capabilities of such a model are much higher than our actual normal linear regression process and stuff, right? Linear regression process is given a points, you just put a line in a way that it can classify them properly, optimally, with minimum loss in classification. After classification regression, you have minimum loss with respect to it, and then we live with it. But um, but we don't know whether we are actually overfitting or underfitting to the expected patterns, right? So the expectation is you're not supposed to overfit. Overfit is good for training data, but what happens is it creates a loss in the test data, or when you are actually predicting with unknown data that comes onto the table. So we should avoid overfitting. At the same time, we should not be in underfitting. So the optimal way in between is the target state for everyone. Okay. That's with the okay. Let's ask ChatGPT. I thought of asking ChatGPT also once, saying, mm, mm, "What is the difference in linear regression comparison support for machines and linear regression develop format? Okay, type. So classification regression class. Algorithm. Okay, type. Linear regression is obviously because I've not considered logistic regression. He's saying regression and classification regression. So we need to find the hyperplane that maximally separates classes or maximizes the margin between classes in a high dimensional space. Okay. Linear regression aims to find the best fitting linear relation between the independent variables and the target variables. Okay. SVM produces discrete outputs, class labels for classification tasks, and outputs for regression tasks. Linear regression produces a continuous output that represents predictions, estimations, or target value. Because he's getting into this so-called regression to classification kind of comparison. So can capture complex nonlinear relationship using kernel functions, allowing for flexible decision boundaries. Regression models a relationship linear, making it less flexible for capturing nonlinear patterns. Okay. Loss function SVM uses a hinge loss function for classification tasks and an epsilon insensitive loss function for regular tasks. mean square error loss function. You know that which penalizes the square difference between the actual values. SVM optimization involves solving a quadratic programming problem to find the optimal separating hyperplane or regression function. Linear regression optimization involves solving a system of linear equations using techniques like uh, ordinary least squares or gradient descent. Okay. Generally robust outliers due to which focus on maximizing the margin between classes. Okay. Linear regression can be sensitive to outliers as it aims to. Yeah, this is the robustness point is actually the square difference between red and black. So that's the robustness is where it is talking about the concept where I said, okay, I think I'm not sharing the screen. Sorry guys, I thought I was sharing the screen. I was reading. So I've asked ChatGPT on what is the difference between SVM and integration provide. So initial point it's majorly focusing on classification and regression capabilities of SVM, whereas linear regression is only regression. I should have asked the question as linear regression and logistic regression, but it's okay. In the robustness, it says SVM is generally robust to outliers due to its focus on maximizing the margin between classes, whereas linear regression can be sensitive to outliers as it aims to minimize the square difference between the product. So, as I said, in this path where you put this in between, if their distribution, these points on how they are distributed and on these points on how they are distributed, impacts the loss function because of there are more outliers, higher values here. Then obviously to minimize the loss, it will come closer to this point so that these outliers that are there, those are also predicted well. Or else what happens is if you don't move towards this class, the outliers will have very bad loss, and because that the overall loss will be higher, and we will try to obviously our model will try to reduce the loss and it will go closer to these points. So it if there are outliers, it would impact the decision. So whereas SVM doesn't get impacted because of going with the margin between classes logic. Regularization SVM can incorporate regularization parameters to control overfitting, such as the parameter C in CSVM. Linear regression can incorporate regularization techniques like. I think we have not covered regularization. Sometime we should also look at regular. I think regularization, bias, variance, underfitting, overfitting. These are all few concepts which actually give solution to are actually help in evaluating how good is your model when it output is. But till now, the way we looked at it, it's like the intelligence or predicting capability itself is a big thing. But after predicting, what happens? People start using it in on ground, and they observe that the predictions are actually not aligning with what their expectation is. The accuracy of the prediction is low. We should also look at how these accuracy of prediction are calculated using different ways when you practically work with models. That is also important. I think these concepts could go in a day or two sometime so that we are having a high level idea on those, and when we do practically, when we sit and do things, we understand this terminology is one thing. Second is also we know how to, when we build a model, we know how to uh, calculate the accuracy or laws or overall metrics in order to classify or compare between different models. Like say I'm using for a given problem statement, I'm using SVM and linear regression. I should be able to have a comparison between these two to say which one is better, right? So how do you calculate that? What is your metrics to compare, right? That all should also be covered. Okay, so that's with declaration. So interpretability. These foundation boundaries are less interpretable, especially in high dimensional spaces or when using nonlinear kernel functions. Linear regression provides easily interpretable coefficients that represent the effect of each feature on the target. Yeah, because we are not doing w into x plus b in as in linear regression. What we are doing is w into like something like phi of x or g of x or k of x or whatever, a function that is applied on x at each point level to impact the points, and then we are doing it. So what happens is the prediction to and relation to x is not linear. That's the difference. So in linear regression it is linear, whereas here it is not linear because the y is predicted not basing on x. The y is being predicted basing on that so-called phi of x or whatever function of x kind of stuff. So and in turn function of x has another relationship between actual x and the function of x, right? So there are like two levels. We are like doing f of g of x kind of stuff. So we are applying two functions on top of x here in SVM. Oh, sorry guys. Okay, that's with SVM. I think it is a little bit clear, but we don't have the details on equations, derivations, and other stuff, and that'll make it a little complicated for sure. So we're moving on. Well, let's look at the next one. Um, as per this guy, he said, okay, this is about G boosting. Okay, anyways, a Bayes is a probabilistic classification algorithm based on Bayes' theorem, and with the naive assumption of features independence, it assumes that the presence of particular feature in a presence of a particular feature in a class is independent of the presence of other features. So, despite this simplifying assumption, naive Bayes can be surprisingly effective in practice, especially for text classification tasks. So, when we consider features x1, x2, x3, x4, x5, and stuff, we usually tend with we look at it with certain correlation between them. So that's the reason we combine them together like w1 x1 plus w2 x2 plus w3 x3 kind of stuff. Um, and we increase those weights w1, w2, w3, w4 in a way that they correspond to each x on how much impact it would make on y. At the same time, we put them together so that if even if w1 rises on x, the remaining will be adjusted in a way that the sum of them actually tries to reach y. But whereas in as per this naive Bayes theorem, which uses the Bayes theorem, here we deal with each feature separately, and then we put them together to achieve y kind of stuff. So Bayes relies on Bayes theorem, which calculates the probability of a class given a set of features p of y of x is equal to p of x by y into p of y by p of x, where p of y by x is the probability of class y given features x. Okay, p of x by y is the likelihood of observing feature x for given class y. Okay, is the prior probability of class y. P of x is the probability of observing feature x. So given set of features, we predict y. So this is that is probability of y basing on given set of features. For a given the reverse way of looking at it, that is means for x to y, reverse way of looking at it is given a y, let's say, what is the probability that the certain feature will be there? Okay, that could also be calculated. Uh, Probability of overall of class y, right? And probability of x is although observing feature x. Naive assumption is naive base assumes that the feature are conditionally independent given the class label. Mathematically, this can be p of x of y is equal to p of x1 of x1 by y into p of x2 by y and so on p of xn by y. The calculation p of x of y are the individual probabilities of each classification. To classify any instance, there is calculate the probabilities of each class. And then based on Bayes' theorem, based on the logistics of mod function, coefficients are not directly interpretable. Depends on the impact of each feature on the target. Robustness less sensitive to variable on features, sensitive to multi-column array and outliers, can handle large feature space efficiently, efficient efficient for large datasets and high dimensional feature spaces. Scalability, because even if there are 100,000 features, we are dealing with each feature separately, like feature one to the whole y. Some somewhere close to decision trees, right? Decision trees also they deal with each feature separately. But here, what we are doing is we are not dividing and conquering it. We are dividing the features. That's all. But we are not dividing the data. For each feature, how does it work? Y works, and then we are just multiplying it here. So, um, okay. Performance was can perform well with yeah, small data sets and in higher dimensional space. Large Z with spaces efficiently. Okay. Once he says high dimensional space is meaning more number of features, like same scalability also large feature spaces. And as a logistic regression, what happens? The calculation and stuff, everything is dependent on that. 1 by e power minus z, and z is equal to wtx plus b. So the more number of x, the longer the y will become, and the calculations will be higher if the features are growing. Whereas here, because each feature to y is being calculated, the equation altogether is not one equation that gets longer. It is just that the probabilities needs to be calculated for each feature, and they should be multiplied, kind of stuff, to understand what is p of x of y. This is nice, very nice. Looking at an example, right? Example applying name-based to a small data set, we'll use a fictional data set with three features: age, income, education level, and a binary diagram indicating whether a person purchases a product or not. Okay. Based on age, income, and education level, whether he will purchase a product or not. The product is unknown, but it's a good generalization saying it could be applied for any product, right? Uh, whether a person makes a purchase based on their age, income, and education level. Data pre-processing, convert categorical variables, yeah, age, income, and education level into number values if necessary. Okay. Then calculate class prices. P purchase is equal to probability for purchase is equal to yes, and probability purchase is equal to no. Um, Calculate likelihoods for each feature, age, income, education level. Calculate the condition probabilities like P of feature of purchase. That is like P of age of purchase, P of income of purchase, and P of education level to purchase. And is the class priors means that is P of Y. Okay. And for age is equal to middle aged, then P of middle aged of purchase Y equal to S, Y equal to no. The calculator. Income level high, Y purchase is equal to Y, purchase is equal to no. Okay. For education level college, purchase is equal to Y and purchase is equal to no. Prediction P of purchase is equal to yes. Middle age high college will be P of middle age plus P into P of high into P of college into P of purchase is equal to yes by P of middle age into P of high into P of college. Of P of purchase equivalently for purchase equal to no. Compare the posterior probabilities for yes and no and select the class with the higher probability. You predict whether the person makes a purchase based on which class. Like we calculate probability for P of yes and P of no, both, and then whichever has higher probability, we lean towards that decision saying whether he will purchase the product or not. Nice. So we covered naive base as well with an example on how it works and stuff. Primary is to understand saying when we have linear regression, when we have logistic regression, why did people create or why did you should think in the direction saying why did people have a need of creating a new algorithms when linear regression, logistic regression are already there. People would have started using linear regression, logistic regression for regression and classification tasks. They would have actually seen some challenges with respect to the calculation or with respect to overfitting or with respect to outliers, data dependency, data set size, and overall performance of computation, all this, and they're trying to optimize it to get better. So in those optimization journey, they are actually picking up different metrics and different formulae or different optimization techniques of approaching the same problem. And that's how I think they've derived all these new algorithms as in SVM decision trees or mm, naive Bayes and stuff, so that they are actually more optimal compared to linear regression or logistic regression kind of stuff. Okay, that should be that should the way we should look at the evaluation. If you look at the evaluation, everything will be clear. Um, we can, if you look at timelines, evolution and stuff, you'll have clear, you can connect the dots on when linear regression has been created, logistic regression, and then when SVMs are created, when decision trees are created, when naive Bayes is created and stuff. Everything has an underlying analysis on what is the challenges with the previous one and why we are going for the new one, and how we are making sure the new ones are better fit, basing on size of the data, basing on the outliers, basing on the need of accuracy with predictions. All these factors will come in, and also basing on the features. Like for example, Naibes clearly says it considers that all features are independent. The correlation between the features is almost zero. They are not dependent on each other. Like, um, this example is perfect, right? Like age of a person, income of a person, education of a person are not directly related. They could be independent. People at higher age can also study. People at higher age can also be rich. They can also be poor. So all combinations of features are possible, and they're very independent. So such kind of independent features, if they are there, naive Bayes is a better classifier compared um, to logistic regression. And also, uh, I would not say comparison between naive Bayes and SVM which will perform well. But again, SVM and logistic regression, they don't uh, look at features to see their independent features. They say they think that the features, overall features has correlation with y, and also within the features they have correlation between them as well, which we don't know. That's the reason they try to put them into same equation so that each feature in turn impacts the other feature kind of stuff. The problem is we treat we don't treat saying x1, x2, x3 are related, and x4, x5 are different. We treat them like all of them are related, and um, having more weight to any of the feature will actually impact one way or the other way the remaining features. So that's how we fine tune our, that's the difference that is on the table. Okay, I thought of covering the k-means clustering as well today, but I think we need to push it for tomorrow, uh, and continue k-means clustering tomorrow. It should not be a big deal. We should be able to complete it, but I think it will be overwhelming to cover more things in this flow itself. Okay, that's all for today, guys. The energy levels look a little low, but I think I'm good. Um, mm, I think uh, we're going at a good speed now compared to the initial days where we are trying to set up more foundational understanding. Um, I should also focus on picking up learning new things, but I'll see. M- but my advice would be if somebody is also following or studying along with me, then my advice would be to uh, uh, get deep. If you have time, get deep into these algorithms, not to understand the algorithm or focus on implementing the algorithm, but I want you to capture the thought of how somebody would have published a paper, right, saying this is called SVM. Then what is the in that paper, if you study, they'll give an analysis saying if you do linear regression, if you do logistic regression, or their current models that are there, if you do them, these are all the gaps, and they would give a comparison to address all these gaps. SVM is the way to go, which will actually uh, address those gaps and give you a better solution. That's how people will evolve. And if you, as long as you capture that evolution, it's not about the linear regression equation or the SVM equation or naive Bayes equation and stuff. It's more about if you capture the evolution, you capture the thinking process on how they have optimized that thinking capability being induced into you, you work with a model which is completely different from what we're talking right now, but that approach, optimizing thinking, or improving at the problem that they faced and stuff, those are all experiences. Those experiences will give you much better intuition with respect to what and in which direction your model should head. um, because applying model these days is very easy. It's just about bringing up a library and passing the features and x and y values with supervised, unsupervised give it x values kind of stuff. So it will take off everything. The um, uh, Long ago we should used to do all the data cleansing process, which used to take a lot of time. Even today we should do it, but it is much easier, faster. It because the algorithms are smart enough to understand what kind of data is there, um, which is categorical data, which is non-categorical data, which needs to be normalized, which need not be normalized. All those factors are being understood by the algorithms itself, and they are doing it on their own. So less work for people, and analysis also, data analysis also. Um, uh, it's called exploratory data analysis kind of stuff. So where you analyze the data, and analyzing the data will help you in creating maybe new features, dropping the existing features or something like that, and also tells you what models would like. When now that you know why we have different models, what is the advantage of those new models compared to the old models, what they can handle, what they can't handle. If you know it, then you make a better choice of models, and then the predictions will be much better. That's the way to go. Okay, thanks guys, see you later.